Nate, you're muted.
Nate, you're muted.
Yeah.
Hey guys, sorry it's muted there. Happy Friday. Welcome to the Telos Reach workshop. The purpose of this workshop today is to go over the SDK that Reach provides for Telos when building and deploying applications, smart contracts on Telos. There's a lot of cool features that this SDK provides, and we want to make sure that our existing developer community is aware of it, and really just build off of this and have you guys feel enticed to use this awesome technology, and just introduce some of these great people here. And I'm going to hand it off to Jesse here to talk a little bit about Telos.
Yeah, sounds good. So hi, everybody. I think some of the Reach community probably doesn't know me. So I'm Jesse, head of engineering, CTO at Telos, and bring you up to speed a little bit about Telos. We launched 3 years ago and did no ICO. So one of the big principles we have is that we have very strong governance. We launched very fairly. It's a blessing and a curse. No ICO money, but no big VCs and big holders to influence things, which again can be good and bad. But we spent the first it's actually almost 4 years now ago we launched, 2018. The first 3 years we have a C++ smart contract platform, super fast, powerful, feeless, very high capacity. And one of the best things that we've done was about almost a year ago as we launched an EVM. So with all of the speed and performance, decentralized tokenomics and everything, we felt bringing in the EVM ecosystem, Solidity, just all the tooling and everything that EVM brings was something that we felt would go very well hand in hand with our speed and our performance and everything that we've been doing for 3 years. So about a year ago, we launched our EVM, which is a fully compliant Ethereum virtual machine, inheriting all the speed. So we have half-second block times. We can do thousands of transactions a second, like 10,000 and above. And again, we don't have big VC whales sitting on half the supply to kind of mess with governance votes and things like that. So putting a EVM on top of it, we actually were able to build an entire Ethereum virtual machine inside of a smart contract on our, we call it native, to compare it with the EVM. So on top of our native network, we have this smart contract that runs the whole Ethereum virtual machine. So kind of a testament to how powerful the smart contracts are at the native level, that you're able to build the whole Ethereum virtual machine, like kind of blockchainception, inception, a blockchain and a blockchain. And so we launched that over a year ago, or almost a year ago. It'll be a year sometime in November. And we've seen the influx of attention and developers that we wanted to see. Everybody loves using it once they get to use it. This year, last month, got a chance to co-sponsor the Harvard hackathon. I got to meet Nick in person and some other folks from Reach, and the fact that it was compatible, and Reach brings in what we're really going for at Telos is that real world adoption. People get familiar with Web 2 look and feel, where how quickly Gmail responds and things like that. So our ability to give half-second block times and really high throughput, we want to bring in, everybody from all reaches of technology to blockchain, and Reach, helps do that, because there's a kind of, they offer that abstraction layer of making it simpler for people to come in and build applications in Web3 on an EVM like what we have. It was kind of a great fit, worked out the gate, because again, EVM compatibility is kind of a standard now in blockchain, and it was just awesome to see people building applications on our EVM with Reach at the hackathon. And so happy to be here with the workshop and help everybody learn about Telos and Reach and how you can combine them to build something great. So hand over to Chris.
All right, I'll go next. Hello, everybody. My name is Chris, if you don't know me. I'm the CEO of Reach. We created Reach, just like Jesse said, is to actually bring in the rest of the developers. There's 25 million Web 2 developers in the world, and there's maybe around 6,000 full-time Web 3 developers, which is nuts to me that we think that Web 3 is going to actually be Web 3 with just 6,000 developers currently doing it. So we created Reach as a full end-to-end development platform, including a programming language, a compiler, a deployment tool, everything that is needed to make blockchain development modern. The language itself is a higher level language that is a syntax of JavaScript, so it's very familiar, easy to learn. And you program at the actual level of the participant. All you say is, Alice does this, then Bob does this, and then through the compilation process, we pull out the smart contract, and we pull out the actual backend of the client to communicate with a smart contract to make it very, very easy to actually learn and develop, and fast to develop as well. We've found that it's about 50% cost savings using Reach compared to actually doing things, writing Solidity by hand. And we're blockchain agnostic. I was really excited to learn about Telos, and I've known about them for a while because they've been in the space for a while. And when they came out with the EVM, that was great because we already output to the EVM, and because they're compatible with the EVM, it just worked, and it was a great partnership there. But like I said, our main focus here is to go all over the world and find those Web 2 developers that know how to actually build applications, but maybe don't need no blockchain development. And we just put the tools in their hands. And this is actually what Nick's going to be showing here in a little bit, how easy it actually is. Nick is one of the best humans on this planet, so you're going to be in good hands with him. But I'm just really excited for this partnership and see where exactly that it can go. So I am passing it back to Nathan.
Yeah, so thanks for those intros, guys. Really interesting stuff. So Nick's gonna dive into some code here, go through some snippets, and you guys are gonna learn a little bit about the Reach language today. Just follow along. At the end of this video, for your developers watching or will be watching, we were gonna have installation instructions, and you can go back and go back through it. But right now, let's just be aware of how cool this programming language is. Go ahead and take it off, Nick.
Yeah, thanks, Nathan. I'm going to share my screen here. So my name is Nick Stanford. I'm the developer experience lead for Reach. And today I want to talk a little bit about developing Web3 applications. So the first thing to think about is that this new Web3 programming paradigm, development is hard. There are a lot of special considerations when we develop Web3 programs that don't exist in Web 2. If you followed Web 3 for any amount of time, you're familiar with this term, exploit, right? An exploit is just a flaw in the code of the smart contract that doesn't account for one of those special considerations. So how can we feel comfortable writing these complex smart contracts when we know that there is no budget for bugs? And what other special considerations are there? Dealing with low-level network native languages, node infrastructure to actually interact with the network, security checks, right? These are things that make it complicated to develop Web3 applications. What if instead it felt like developing a regular Web 2 application? What if the language already felt familiar to the most popular web language today, JavaScript? And what if you could guarantee that your program didn't have any of the common flaws that smart contracts see today? What if we built a platform designed to deal with all of the special considerations for Web3 applications? Reach, a blockchain development platform built for developing your decentralized applications for Web3. We know what tools you need, so we built a platform to give you those tools. It's the highest level of abstraction in blockchain programming, lowering the barrier to becoming a Web3 programmer, and at the same time, raising the ceiling of what is possible with this new technology to actually bring blockchain mainstream to a place where it can change the world. So what exactly is Reach? As Chris said earlier, it's made up of these three key pieces: a programming language, a compiler, and a network deployment tool. So the programming language is modeled from JavaScript, so it feels familiar, making that transition from Web 2 to Web 3 easier, lowering that barrier. Second, the compiler, an auto-formal verification engine. What is that? The verification engine uses the logic of your program to create mathematical proofs to verify your smart contract against vulnerabilities or flaws. At compile time, Reach will use a system of equations to check all possibilities related to your program. What if all users are honest? What if none of the users are honest? Reach will check all of that for you. There are a number of built-in checks, but you can also specify custom checks related to your program. And we'll look at some of those when we get into the code. Third, network deployment tool. The deployment tool actually allows you to deploy your code to different blockchains without any extra node infrastructure. For Telos development, we'll simply set Reach to point at EVM, and then point our MetaMask to the Telos EVM testnet and deploy our application. That's how simple the network deployment tool makes it. But Reach developers can think about their applications in a more simple and abstract way. Reach developers don't write smart contracts. We write Reach dApps, and we let Reach build us a smart contract. That is the abstraction. You define your Reach app based on how your users will interact with the smart contract, and Reach will compile it down to smart contract bytecode for you. You focus on the business logic of your program. What does this user need to do? Here is an overview of that Reach app. And notice it's actually producing a smart contract for you to send out to the network. And the deployment tool will take care of that when you're ready. Reach supports Ethereum and its layer 2s, including Telos. But what exactly does a Reach app look like? Pull open our VS Code window. VS Code, Reach has custom extension support for VS Code, so you can actually develop inside an IDE that you're likely familiar with. But what does a Reach app actually look like? Let me scroll down a little bit here to what we refer to as the business logic. So on line 81 here, we can see that user 1 only, go do something, right? If you haven't seen Reach before, you can probably look at this code and tell me what it's doing. User 1, publish this information, and then pay this. Business logic. What does your program actually need to do in terms of your users? And then just tell it that. User 1, publish this information to the blockchain, and then pay that amount into the contract. There's a lot of functionality packed right into these two lines. That's what we mean when we refer to business logic. So no longer do you have to look at low-level machine code or network native code. You can think about your application in a more abstract way, on a higher level. What does this user need to do? Well, this user needs to tell me what is the wager. They need to tell me what is the deadline. And then we need to tell that to the consensus network, to the blockchain, right? And then we need to pay that amount. And this is the simple business logic that comes along with writing Reach applications. Okay, but what about actually deploying this code? So this is a full application that I've written. And what if I actually wanted to deploy this code? So I'll go into the folder where it lives. I'll export the Reach connector mode. Remember, Reach works with different blockchains. So at this point, we need to tell Reach, where do you want to look at? And right now, for layer 2 conversations, EVM conversations, ETH all kind of fits into that. So we say, export that Reach connector mode to the Ethereum or an EVM style network. And then we use a simple React tool to say Reach React. Now, this tool will actually spin up a React development server right here for you and package everything you need for your Web3 application. So we'll let it do its thing. We'll let it spin up its development server. And then I'll show you quickly how we can actually take this to our web browser and actually test it live. We'll give it a second to finish up setting our development server here. Great, no errors. We've compiled successfully. We're going to grab this localhost link. We'll open a new window. And we're just going to paste it in here and say run. Okay, this application has 2 users, so I'll bring up 2 terminals. I'll 2 browser windows here. And I'll just let MetaMask tell me which network am I pointing at. We tell it right here, point at Telos. Run on the Telos network. All right, we've imported this into our MetaMask beforehand, right? So now we'll start the game here, and I'm going to set some number just so that we can see it on the other side as well. We'll deploy. Remember, it'll actually send that out to the blockchain for you. We see that we've got some estimated gas fees, the amount of tokens it costs. We'll confirm. And then on this side, we're just going to allow that second user to attach to the application. There are different ways that you can make this work. In a real application, maybe you put this under a QR code or something else. But for demonstration purposes, we'll paste that contract address here, and then we'll attach to it. And now we see we have that same set of terms on the other side. All right, this is us actually going from VS Code to the Telos testnet live in 30 seconds, right? So we could step through and work through our game here. We'll see that we're spending Telos test tokens here, right? We can work through this whole game, but that's not the purpose of this, right? I'll confirm that transaction, and we see that this game would run. We should get on the left here, we'll get a couple numbers that pop up, right? We could start to run our game here. So that's how you move from your IDE and from like testing your code up into the testnet quickly and easily with Reach. But this game, if you're not familiar, Mora is a very old game, but this game has a function that it computes the winner of the game. So this does not fit into the automatic checks that we referenced with Reach. Remember, Reach will check things automatically, but it doesn't know about what custom function you just wrote. So let's take a look at that function. We'll come up to the top, and we'll see a very simple function here we're calling winner. Here's the name of the function. Here are the inputs that it takes. And then here's just some basic if-else logic to tell us what exactly it should do. Now, if you're writing a complex function like this that has a lot of different possibilities for outputs, for return values, you're maybe familiar with testing this in different languages or other environments where you're just going to test all your different inputs. You're going to say, okay, what if I pass it this and then I pass it that? Do I get the output that I want? Does this input register that output? And you have to test that as a developer. But what if there was the verification engine could test it for you? We see here in lines 26 through 30 what those edge case sort of tests or what those tests look like. I can tell Reach, assert that when I send these inputs to the winner function, that I get this particular output. Check that for me. I want to be very certain that this is how this works. And you can do so for different types of inputs, but it also allows us to do more powerful things. Like line 33 here, you'll see for all uints possible in A, every number that is possible for A, every number possible for B, C, D, pass all of those in as inputs to this winner function. Check all the different possible combinations that exist given the data type that I'm showing you, and tell me, is it some outcome? Is it what I expect? Or is there some flaw in that code that would behave differently than I expect? We use these asserts to tell Reach about our assumptions of the program. I assume that when I put in this set of inputs, that this is the output. And I let Reach guarantee that for me. Now, we may think this application, this is a test application, it's a game, right? It's similar to rock, paper, scissors, much older game. But the repercussions here, if we get this wrong, are pretty low. You know, maybe Alice loses 5 tokens and we got it wrong. But what if this function was handling millions of dollars. What if this function had serious implications for large amounts of value? How comfortable are you in your logic then? And what if you could tell Reach, check all of this for me and make me feel comfortable with it? So when I run this application, Reach is going to check those asserts for me. I'll just tell it Reach compile, and it's going to check these asserts for me. It'll check all of the automatic ones that we input. For example, a good automatic check is, are there any tokens left when the contract tries to exit? Right? This is one that pops up. Funds locked inside of smart contract, no longer accessible. Reach is checking that automatically at compile time. Is there any way that this is possible? If no, it's not going to compile for you. So you'll see verifying knowledge assertions, things that I assume are true about this program. We'll verify for the generic connector, and then we'll check when all users are honest. Are they staying within the bounds of what we've said as a program? Or when no participants are honest, when no one is honest, what if they throw caution to the wind and give us any value outside of what we're attempting to control? Reach checks all of that for you at compile time, including the custom checks that we've specified here. Assert that this is true. And you know, if Reach comes back and says, I checked 80 theorems and there were no failures, now you know that function behaves exactly as you expect it does. Exactly as you expect it does. So this is a very big deal when you start moving into larger applications, production level applications, where you need to test what you assume is true about your program. So what if instead we were to write this as a Solidity application? What if I wanted to write this same game, this Mora game, as a Solidity application? Reach has a special feature here that's going to allow us to look at what some of these files look like. We'll tell it Reach compile the intermediate files and show me what those look like. So Reach is going to do the same thing. It's going to check all of your theorems, but now it's going to output some extra files to our build folder. So I'll come in here into my build folder and I'll see all of the files that were output. The one I'm really looking at is this main file here. We'll bring this down. Now, this is the generated Solidity code that comes from the Reach full DApp. This is what I mean when I say Reach is generating this for you and outputting it. You don't typically see this unless you ask Reach, hey, can I see this? So if we look at our Reach code, I'll jump to the bottom. It's 175 lines of code, 176 lines of code. And I comment well, so there are a lot of comments. But let's look at the Solidity code. And we'll scroll down. We'll continue scrolling until we get to the bottom of this file. This file is over 1,000 lines long. This is Solidity code that you did not have to write. Consider how much time that saves you alone to write a 170-line file versus a 1,000-line file. You'll save time on the length of your applications. And further, you'll save cost on the audit of your applications because auditors spend less time auditing Reach code. It's shorter. They know that it's inherently secure. There are things that are automatically verified. So not only is your time saved by writing shorter code, but now we can think about pushing forward what it means to have a real Web3 blockchain application. We're not copy pasting some code from some repository somewhere that does something that it's always done. We have the power to build the next level custom application. Why? Because we're not wasting time on the other 825 lines of code. We can spend that time developing advanced features for our application to take blockchain from where it is now to a place where it can actually change the world. That is the power of using Reach. So I've talked a lot about the power of using reach and looked done some overviews at what comparisons look like and the simplicity of the tools. But now I actually want to walk through some of the language with you. I want to show you what it looks like to think about an application and then build it right here live. And I'm actually going to build a few different ones. The application we're going to look at today is an RSVP application. Buffy wants to have a party, but she doesn't want to charge any money. She also doesn't want too much food. So the solution asks guests to stake funds. If you're going to RSVP to my party, stake 1 token. If you don't come, I'm keeping that token. If you do show up to the party, I'll return your token and welcome you into my party. Okay, so this is the overview of our RSVP application. Here are 2 different ways that we can think about building our application. On the left, you'll see number 1, a DDApp, right? A very decentralized application. There are levels of decentralization when we talk about controlling the data or the instance of the smart contract. The left, the first one we're going to look at, is very decentralized. It's very decentralized, short, compact, and does exactly what you need it to. And then the second application we'll look at is a little bit bigger, a little bit more of a production level application, and what it would look like to manage this in sort of a real world scenario. Let's jump back to our VS Code window. We have our RSVP application. So we're going to start by looking at the 2 different files that come with our Reach application. Let me make sure I'm set up here correctly. So we have 2 different files that start our Reach application here. We're looking at .rsh. That is your Reach code. You say, Reach, what version are we working with? We're working with 0.1. We'll set another global here, let's say use strict, and we'll get into that a little more. But these are the 2 files that exist. You have your backend RSH file, and then you have a front end. We show JavaScript, but you can use any front end language that you like. Python is another popular one that people use. And we'll actually just import that backend here to our front end, right? This is our full Reach dApp. I showed that image earlier, full Reach dApp. And then this will break down into a smart contract. So I'm not going to show this test code, but just know there's some test code that lives here in the front end. I'm generating users. I'm running sort of standard tests based on our application, but I really want to focus on what the Reach code looks like. So if we have an RSVP application, there are likely some details about this application that we need to share. So we'll set the details as an object, and then we'll just tell Reach what those details are. Well, there's going to be a name, and we'll say that we'll just declare the type here. It's bytes 128. We're allowing 128 bytes for the name of this event. So the next thing we'll show is that there's a reservation cost. Remember, Buffy wants to charge people to come to RSVP for the party and then return it. So Buffy's going to tell us what is that reservation. And right now we're just specifying its data type. We're specifying our data definitions. What type do we need to use? There's also a deadline to this party. You must RSVP by this time. And that's also an unsigned integer. It's just a number. And then there's a host. And host is an address type. Address is a special type in Reach. Again, we know that you need to use that, so we created a special type for it. And now we'll actually start getting into a little bit of the meat of our Reach code. So this is the actual export for your Reach app. We'll say export const main equals a Reach app. And then we'll dive down into here and make sure that we don't have any syntax errors. This is not a good time to have syntax errors. And now remember, we're just going to focus on our users and how they communicate with our application. In a very decentralized application, there are 2 users to this. There's a host and a guest. And then each time we'll create a new instance, right, in agreement between those 2 people for their application. So if we have a host, we'll just say const host equals a participant. We'll call them host. And now we're going to define what are the things that we allow hosts to do. right? If we have two different users, one will be the host, the other will be the guest. We'll say guest is a participant, and we'll say guest is the name of that participant. And now you see we've got two areas that are specified for our two different types of users, the host and the guest. And now we can isolate what they're allowed to do. I can say that the host is allowed to provide the details, and the host is also allowed this Boolean value that I'm calling showed. Did the person show or not? So these are the pieces of data that we're allowing for that user. When this user comes in, they'll be bound to the host. This is the only user allowed to do those things. And now we'll look at the guest. And the guest is also going to tell us what details do you think are for the party you're arriving for. And then what they'll be allowed to do is actually register. And registered is a function. It takes in one value for the contract value, and it returns null. So you see now that these are just the signatures for what we're doing. Registered is the name of the function. We've denoted it as a function, and here we're specifying its inputs and its outputs. Okay, so we've defined all of the data that is necessary for this application. That's it. That's all of the data definitions we need. And now we'll tell Reach, init, start stepping through the actual states of my program, where we tell our users, user one, go do this, user two, go do that, right? So in this instance, we're going to allow the guest dot only to create this for us. The guest is going to tell us, hey, I'm ready to RSVP for this party. And they're going to tell us what the details of that party are. So we need to declassify this information as it comes over from the front end hashed. And then we'll set it to the object details. And this comes from the front end. This will come over from the front end. We'll store it here. And now the contract or the user has set this value. And we need to tell the consensus network. We need to tell the blockchain about it. We need to say guest.publish. Publish just means publish this information to the blockchain. Write this in and say that this is the value for that identifier. So we've published, and now we're going to .pay. What do we need to pay? We need to pay the reservation cost. That's stored inside of the details object. So we'll use the dot operator to say pay details.reservation. And in these few lines here, we've gathered all of the information we need about the details. We've published it to the consensus network, and we've paid some amount into the contract account. So now we've paid into the contract account. The next thing we're going to do is grab some of those details, right? So if we want to unpack those details, and so that we can reference them individually. So instead of just referencing the details object, I'm going to unpack everything that's involved and allow us to use that instead. So I'll say equals those details, and now I can reference these individually. So I'll start with my first verification check. I'll enforce, and this tells Reach, enforce this thing. If some user comes in and tries to register, the deadline's already passed. So we want to tell them, too late, you can't register. And all we need here is some condition. We'll use this reach function, this consensus time, to go get the consensus time for us. What time is it? And then we'll say, is that less than the deadline? If that's false, return that it's too late. Okay? And now we're just going to notify the front end that the guest.interact has registered. And then we'll pass a contract value in there and then get contract. We'll commit to this information and we're ready for the next step. The guest has told us what are the details about the RSVP you're trying to RSVP for. We've told the consensus network, we've paid that into the contract, and we've grabbed all the information involved with that details object. We're committing to that information. And now the next step of our application. We want the host, and let me roll up a little bit so I'm not too far down. We want the host dot only to do something. Now it's the host's turn to interact with the smart contract. What does the host need to do? The first thing the host is going to do is check some details. So we'll give it this other constant name here, h details, and we'll say declassify those details. And then I want you to check, are those details equal to these details? If no, return wrong event. Tell me, sorry, you're at the wrong event, and allow my application to continue. We'll say const showed. And this is just going to hold a Boolean value. Did they show up or not? Interact.showed. Okay, so we have the host providing some information for us. So we're going to use host.deadline, or I'm sorry, host.only, and then we're going to go in and we're going to check some of that information. So now the host only do that thing, but now the host needs to publish that information to the blockchain. What information? Well, showed, and then we'll check based on this. What are we checking? We want to check this equals the host. And don't get too caught up. This just refers to whoever's calling your application. What is the user's address that's calling your application? So now I can check, is this caller equal to the host address, and just reference it that way. That's all that this pointer does for us. And now I want to enforce again. Is this consensus time greater than or equal to the deadline? Because you're too early. And here we're specifying custom checks for our application. And now we know whether or not the user came into our party. And we can transfer the reservation to who? Well, that depends. Did they show? If yes, transfer to the guest. If no, transfer to the host. And then we just want to commit to our information and exit. And that's our full RSVP application in a very decentralized way that will create one instance of your smart contract for every reservation that exists, right? Every time a user tries to RSVP, it's going to create an instance of this smart contract. We'll walk through the logic again quickly. The guest only, tell us the details, and then tell the consensus network and pay your RSVP. Let's talk about those details a little, and then let's let the host verify, are these the right details for the party that I'm hosting? We'll enforce that the deadline is not passed, and then we'll transfer the reservation to the host. We've done this in 44 lines, created a full-scale RSVP application. I don't see any errors. Kind of glance back through it. Luckily, I don't see any errors. So let's pull it up and see exactly what it does. I will reach compile. Reach compile is going to check your RSH file for any errors. This is a simple application, so we've only got 9 theorems that we're checking, and there are no failures. I'll export the reach connector mode. And then I'll say reach run. Now this will run locally right here inside my, my command line environment. And we'll see that several users made their reservations. We're going to wait until our deadline, and let me scroll back up here. Several users made their reservations. We see different addresses for every user. We're going to wait until the deadline, right? We specified a deadline. We need to wait until that deadline. And now we're going to start checking in our users. We'll check in. This person did show. This one did show. And then we have this check here, where someone tried to show up to our party, but they didn't register. No reservation. So this is going to allow you to return that error, say error, no reservation, return that to the caller and continue on with your application. We'll check in a few more users, see if they did or did not show, and then we'll check our transfer pattern. Anyone who showed up to the party should be even to what they had before, and anyone who didn't show up to the party should be -1. So you see here we've got different transfers for each one. Jonathan didn't come. He's got 100 on the dot. He's got no reservation. So this is what it looks like to think about and how quickly we can go from the thought of, well, we need an RSVP application. Okay, how do people interact with an RSVP application? Well, user 1 does this, then user 2 does that. And we've been able to write that fully functional application in 44 lines of code. And if we were golfing, I could probably get it down a little bit lower than that. 44 lines of code. But what if we thought, okay, that's a lot to manage. Remember, if we go back to this slide here, we look at the left, the dApp that we just produced. The host has a lot of work to do to manage all of these guests, right? They're going to have to manage each instance of the smart contract, but the dApp is super decentralized. It's very decentralized in the way you think about that. But what if we instead thought about it in this version 2? In point 2 here, we say there's one instance of the dApp, there's one instance of the dApp that the host can manage in a centralized way. One host managing all of the guests. That's how your RSVP application would likely look if you were thinking about this in more of a real terms. So what does that look like if I were to build that in Reach now? Let me pull open my next file here. Be ready for you. So now we're going to completely reimagine this. I'm starting from scratch. I've already built one application in 20 minutes, and I'm starting from scratch. I'm going to build a completely another application, a whole nother application. And this one's going to look at the more realistic way of that maybe that you would actually manage this. If I was the host, I would want one instance, and I would want everyone to interact with that one instance. And this is going to get a little bit closer to what a real Reach application would look like. And I say real, the previous version works as well. It doesn't, I mean, it is a version that works exactly like we expect it to, but there's more management than we would want. So how do we then streamline and think about making this an efficient, super useful Web3 application that's not clunky, that's like one instance, and we manage that as one event, right? So we'll specify the same details object. We'll say that name is, it's some string of bytes, maximum 128. There's a reservation, and that's just some number. And then there's a deadline, and that is also some number. There's a host, and we've said that that's a special type in Reach, address, right? We know you need to use address, so we just created it as a type. And now we're going to do the same thing we did before, where we're going to say export const main equals a Reach app. Okay, make sure we don't have syntax errors. And now we're going to think about our users in a little bit of a different way. Now, there's still going to be a host, an admin, someone who provides the information and then allows other users to check in. So we're still going to have one participant, and this time we're going to call them admin. We're going to say admin is a participant that we're going to call admin. And I see that syntax error. I'll correct that here in a second. Got to make sure we spell. We can program well, but if we can't spell, we can't program. So here we have that same syntax we saw before. There is one user that is going to be the admin of this application. And what are we going to allow them to do? We'll say, give us the details, and then let us know when the contract is launched. That's a function. That's what this fun denotes here. It's a function. It takes in one argument, which is a contract value. And then it also it returns a null value. Again, this is just your signature. The name of the function, what is it, inputs, outputs. If instead you just wanted to say that deadline was some number, that's what this is doing on line 7. Deadline is some UN. And we've specified deadline is some UN. And then in the front end, we've actually provided what that deadline is. I'll come down here a little bit. Yeah, so we see that here is that details, that set of details. And that's where we're actually providing the value that is the unsigned integer we're referring to. Reach programs mirror the back end and the front end, they mirror each other. So on the back end, we say, oh, details is this object with a name, a reservation, a deadline, and a host. And then on the front end, we say details is this object, and then we've assigned these values some real value, some number, some address, right? And then we're passing that back to the back end and saying, okay, here is that information I told you about. So we've specified the admin participant, and now we're going to look at the next level sort of reach code, where we say, what if instead of binding one address to the admin participant, what if, like in our application, we have many different users that all need to do the same thing. We don't have to specify a participant for each user and say A, B, C, D. We can say, let's repeat the functionality that I'm allowing for a guest. We'll say this one is a guest, but we'll specify them as an API, and we'll call that guest. And now what is that functionality that all of our guest APIs are going to be allowed to do? The only thing that will allow them to do is register. And register is the name of the function. It takes in no inputs and it returns a null value. That's the only thing that guest is allowed to do. But every instance of a guest can do that thing. We don't have to spin up new participants for every user. We can say, here is a set of users where we need to repeat the functionality. So we say guest is an API. And then the other API we're going to allow in this case, we'll say const host equals an API. We'll call them the host. Now, I know that the admin is sort of technically the host, but I'll show you why we're sort of specifying this in a different way here. We'll say the host is an API. And what is the host allowed to do? The host can check in users. So the host can check in people coming to the party. Check in is just a function, and it takes in some number of inputs and it returns a null value. Now the check-in function is going to take two inputs. What is the address of the person who's trying to check in? And then a Boolean value that says yes or no, they're here, true or false, they're here. So in the same way that we did before, we've specified who the users are in our application. This is the way we think about Reach applications. Who's using a smart contract? What are they allowed to do? And then we build our application like that. So now we've said these are the three types of users. There's an admin, a guest, and a host. So let's start stepping through our application. Remember, init is like, let's start stepping through the states. I'm done defining data. Let's start stepping through the states of our application. So I have this init call here. Now I'm going to step down into the states of my program where the admin only is going to give me some information. Admin only, give me some information. This case, we're asking for details, where details is declassify, interact with that front end object that we've specified, we've called details, right? You don't have to declassify this information. You could hide this information if you need to. That's also a feature in Reach. But for this demo, we'll keep it public. We'll work through that details information. So we've got const details. We'll bring that over from the front end, and then we'll tell the admin publish, if we spell it right, the admin publish details. And now the consensus network knows about those details. So admin publish the details, and now let's unpack them from that object so that we can use them. We'll say const, and then what were they? They were reservation, there was a deadline, and then there was a host. And that's coming from the details object. We're just unpacking each of the pieces of it. So we'll take those details, and now again, we'll say, well, enforce something for me. Enforce that this consensus time is less than the deadline that we've specified. If that's false, return that it's too late. Okay. So we've put this check in that it cannot be past the deadline, or it will return that it's too late. And the next thing we need to do is have our admin say interact and with this function that we've called launched to let us know this contract has launched. Right? And get contract will return the value or the information about your contract, the details about your contract, so that you can show it in the front end. And maybe this is where you like put it underneath that QR code. You get those details, you put it underneath the QR code, and you ask your users, scan this to enter our DApp, or to enter this instance of our smart contract. So we're notifying the front end here that we've launched. Here's the information about our contract. And now we're going to look at the advanced features of Reach, some of the differences between these two styles of application. I do want to really specify, the more advanced features you put into a Reach application, the more condensed it becomes. because again, Reach knows what are the common smart contract cases. What is something that you need to do repeatedly? Okay, this is one of those functions where we're going to say, here are two identifiers that we're calling done and how many, and it's equal to a parallel reduce. Unless you're familiar with Reach, you're probably not familiar with this data structure. But parallel reduce is a key abstraction in Reach. Why? Because the parallel reduce knows this very common instance of what's happening in your smart contract. It knows that there's some set of values, in this case, done and how many, that will need to be updated by any one of these unique users. Remember, we're saying we don't care who that user is. We're allowing them to do this thing, and that will be repeated amongst different users. So how does Reach update the state of your application when the possibility comes from 10 different users? All of those users are trying to update the state in parallel. So how does Reach take that parallel reduction and actually package it into a nice, useful data structure that you, the programmer, can use? It's called parallel reduce for that exact reason. Here are the values that we're going to try to update, that we want to be able to uniquely update with each iteration of our API calls or different users that come into our application. It's really just an abbreviation of a while loop. So if I say, these are the values that I want to update with that while loop, I also need to say, well, there's some while loop condition. And hopefully we're familiar with while loop conditions, but this is just going to run until this condition breaks. So it'll say, well, not this expression where done is just going to evaluate. And then we want to also check is how many equal to 0. Now, this is our exit condition. This is Reach saying, here are the values I want to update. Here's the while condition. Okay. And every time we bring a user in, we want to store their address in some data structure, right? You can probably think off the top of your head of a few that may be useful. But what if there was a simple data structure that was good for this type of information storing? And in Reach, we just call it a map, new map. And we'll say guests, I'm going to pluralize that because there will be more than one. We'll say guests equals a new map. A map, if you're not familiar, is a key value pair. It stores a list of key value pairs, where in this case, we're saying the key is the user's address, and the value that we're storing is some Boolean. Okay, we'll specify what that Boolean is later. But now we've created the data structure where our users are going to come in and we're going to store their information. And now we've also created the looping structure that allows those users to come in until our condition breaks. What are we allowing them to do? Remember, if I show you the guest API, the only thing we're allowing the guest to do is register. So we need to specify what does the register function actually do, right? Here, we're only specifying its signature. What is the name of it? What types are the inputs and outputs? Next, we need to tell it what is the actual code to execute when we call register. So we'll come back down here to our parallel reduce structure. I'll come down here and say .api. The underscore just denotes a special type of API. I won't get too far into detail here, but just know it's another level of abstraction from Reach where it makes it a little more simple for you to write your programs. So we say, here's the API function that we were talking about. And then we say, whose API was it? Well, it was called guest. And what was the name of it? It was called register. And then what are the inputs? There were no inputs, remember? And then we're going to specify what does it actually do. So now we've got the name of it, its inputs. The next thing we want to do is include our updated values. So with this parallel reduce structure, remember, we're running a while loop. But because of security in Web3 programs, we need to be very certain and have a lot of control around where we update loop variables. There are many cases where a loop could get out of control and do many bad things in a Web3 program. But Reach puts tight restrictions on where we can update those values to protect the security and the potential for exploits or flaws. So here we'll actually update the return value. We'll say return. And what values are we updating? Well, it's done and how many. We set up here, these are the two initial values we want to try to update. So when this guest.register, what do we want to do? Is done? No, that's not done yet. And then how many should go up by 1? We should say increment how many by 1? We have 1 extra user. Okay. Now, the next thing we want to do is specify our actual return function. So this return is going to update these values for you. Okay. Now let's actually specify our return function. Now I'm going to do a little bit of just cut and paste here. I think it's easier to show as a demo that way, but that's not actually how I write the code. So make sure I don't have any errors in the way I'm setting this up. I think I may actually. Yep, let me make sure I have this correct. Back up a little bit. So we're going to specify what is the return, right? I showed you where we update those values. And here's where we're going to look at specifying that return. So in this case, because of what I said about the abstraction of this API, this is a pay expression. What I'm going to state right here is that whoever calls guest register needs to pay our reservation. It's all tightly packed right into that return statement. You don't have any extra syntax. We know that one common thing that you need to have happen when someone makes an API call to your application is that you want that person to pay something. So we've specified this place here. You just tell us how much you want them to pay. And this will pop up their wallet UI and say, pay me whatever that amount is for reservation. Okay. The next thing is your return function. Okay. This can trip you up a little bit, but it's a little simple when you think about it. Return just creates a function that we must call with the return value. What is the return value? Guest register? For guest register, the return value is null. Okay, so we need to send that back to the caller. I'll say return null. And this will actually send that null value back to that initial function that made the call. Okay, if you want, the other common to call this is like K for continuation, and then you would have to call that K. And now you're saying, okay, here is that return value that I've specified, and now it's set to null. Okay, I'll add back the return that I mentioned earlier, where we're just updating those values. How many plus 1? We've seen here that we're saying these are the two values I want to set. I want to set done and how many. I want to set them to false and 0. And here now we're saying update those values. The iteration of this call is over. Update those values. Great. So we've made our return, right? We have the signature of our function. Here's the name. Here's the inputs. Here's the return value. Okay. We've paid the reservation. But now let's actually say that our guests map, remember the map is going to store our users. So we'll say guests sub this. Remember, this is just the caller. Okay. This is very important in API applications and applications where we're allowing these API calls. We don't know who that caller is. We've said that it can be anyone. This refers to that caller. So it'll grab that address and it'll say this and then give that specific address is true. So the value, or I'm sorry, the key is that user's address and the value is true after line 37 here for that specific address. The next user comes in, the key will be their address, and then their value will also be true because we're setting it so here, right? So now we've given it, what does it actually need to do? But remember, we want to check things with Reach. Reach has this powerful verification engine underneath of it, and we want to check certain things. We want to check, we want to say, are we done? If we're done, return that the event has started. You can't register. The event's already started. Okay. And the next thing we want to say is check. And we want to check. Remember, this is how we look at users in our map, right? We've stored everybody in our map that's here. So now we want to say, check, is this address in the map? If yes, we'll say, you're already registered. You don't need to register again, right? But Reach provides this special function where it will say, is none. We'll say, is none. And what this does is it actually checks the map for that address. It'll say, is that address in the map? And then return a Boolean value based on that. And then if they are in there, it'll say, this user's already registered. They don't need to register again. So that's the verification engine and how you use it in these like custom applications. How do I think about what is or isn't allowed? And then just tell Reach, I don't want to allow people to register if we're done. I don't want to allow people to register twice if they're already in the map. So you just tell Reach, check. One line, check this for me. And it will check and return that value if there is some error that, no, that doesn't work, right? So the last thing we want to say is when we come in here for a reservation, we want to enforce that this consensus time is less than the deadline. And this is the same check we've used kind of in a few different places. But we wanted like check against our deadline. We told the contract, here's what your deadline is. And now what I want the contract to do is come back to me and say, we've passed that, this user cannot register. And that's what these checks are going to do. This enforce specifically inside of that API call. So now we've enforced, we've set our user inside a map, we've returned them to that null value we discussed. And then we've updated what our actual loop values are. And that's the guest register function. That's the whole function. Okay, now what if, now instead of what if, let's actually describe the other API we had. The other API was this like host.checkin. Remember, that's up here. We can just go up here to host. What is who is API are we talking about? What's the function name? And then what does it do? So let's go down here. We'll say host.checkin is the name of the API, but this time it takes in two arguments, guest and then showed, which is an address and a Boolean. So it'll take in those two inputs and it'll say return. Now remember, this first one is the pay expression. What if I want to pay 0? I can just say 0 and then the return function and say, okay, we're not going to ask them to pay anything, but I want to return whatever's inside of here. And again, if we go up, we would see that return for check-in is null. So we'll put return and then null here. And now what is the benefit of doing it like this? Now, what if you wanted to place this return value first or last? Like your application needed you to return right away and then do some set of instructions. We can put that return value right at the top of the call. As soon as they call, return them something. Or we can come down and do something and then return, right? So we can move that return function and that call wherever we want. This is powerful when you start to develop more production level applications. So now we've specified what is our inputs, we've specified what is our output, and we've told the user, here's how much you're going to pay. We want to, when a user checks in, what do we actually want to do? Here are the values, again, that we're updating all the time, right? This is done and how many. This is what the parallel reduce is for, to keep track of these values. We want to say done is true, and then how many -1. So we're decrementing. We're counting down to 0 until we're out of users. So every time someone checks in, we'll go down 1. And that will fall right in line with our while logic that says how many must equal 0. So we've got that updated value. What are we actually trying to do when a user comes in, when they check in? We want to transfer their reservation to who? Well, we need to check whether or not they actually showed up. So we'll use that Boolean. We'll check if they showed up, send it to the guest. If they didn't, send it to the host. Okay, so what now? What else do we need to do? Well, we've got them in that map. It'd probably be good if we delete them from the map. It's a simple call to say delete sub guest. Remember, guest is that input where it's taking that address, and then we're saying delete that guest. We're done with transactions with that guest. Delete them. And then we'll add and enforce here. And we've seen this one a few times now, but we'll enforce that this consensus time, this time is greater than or equal to the deadline, right? Remember, this is like we're ready to start partying, right? We're at our party, we're ready to start partying. If you try to check in before the deadline, you're too early. So we'll return that error message to you and say, you're too early, come back later. So now we've specified what is actually happening when our user comes in. The last thing is to add some more checks. How easy are these to write? Write what you assume is true about your program. Check that this is the host. If that's not true, return me this error. This is not the host. And the next thing is check. Remember, it's guests is our map, sub guest. And we want to check if there is some reservation. So if they're not there, we'll say no reservation. And again, we'll use a special reach function to check the entire map for that guest. And it's called isSum, where it just says, is it some member of this map? And it'll evaluate to a Boolean value for us. And then it'll tell us, is some guest? And if no, we'll say, okay, you don't have a reservation. I'm sorry, you cannot come to our party. So we've got the two APIs. Look at the functionality here. Look how few lines we've used to define what this application does. I mean, these are the two key functions in this application, and they eat up about 20 lines together. And it will allow you to manage this in a realistic sort of way. So then we'll say reach commit, and we'll say reach exit. But there are opportunities, as I've said, with these loops for things to go wrong. There's an opportunity with each iteration of this loop for the value to go awry, for certain things to go awry. What if reach had a check specifically for your while loop? Spoiler alert, it does. You'll come down here, and before your while loop, you'll say invariant. Okay, we're familiar with variables. Invariant is just something that doesn't change. And in this case, we'll say, here's something that doesn't change during this loop. This is a security check. I can tell reach, I know that this doesn't change. And maybe it's like the balance of the application, and this balance is actually going to give you the contract balance. It'll say is equal to how many times the reservation, right? And that's just a little math to actually give you what the actual accurate balance would be. And if that's false, tell me the balance is not accurate, or balance accurate, that's false. So now we've used the power of reach, and I shouldn't include that. We've used the power of reach to say, I know this about my application. Can you verify that the balance is what I think it is? And it'll actually track that balance for you. And the other thing we're gonna allow it to say dot invariant is guests, our map, dot size is equal to how many, right? That's the number we're just incrementing for when users come in. So we say invariant, the size of that map is equal to how many. And then what if that's false? We'll just say how many accurate, and we'll return that. So now we're allowing reach, and again, we shouldn't include end of line character there. We're allowing reach to verify the assumptions that we have about our program. I assume that this map will not be any bigger than the number of users. So I tell it guest.size equals how many, and it will guarantee that for me at compile time that this is true. Okay, so we have now our full production level RSVP application. I have 60 lines of code. 60 lines of code, couple spaces, but let's see if it actually runs. I'll come in here and I'll move into the folder that I'm in. I'll reach compile just to check my RSH code. Check my RSH file, make sure that there are no errors. Okay, we get a few warnings. Reach will put out a lot of good warnings about the different data structures you use, and maybe some specific warnings about the network you're focusing on, and what either the limitations or considerations must be. Reach has a lot of those built in. It'll just spit out a warning and say, hey, warning, don't do this, right? So let me make sure that I'm pointed at the right network. I'll say export the reach connector mode. I'll spell it right. And pointed at an EVM style network. I'll say reach run and see what happens. This is a full scale production level implementation. There are a few small pieces that we could add on top of this to really bring it home, but it does everything that we talked about in 25 minutes. Everything that we talked about in 25 minutes. So we'll come up here and we'll look and see that this is the test code. Remember, I said there was some test code. I didn't show too much of what the test code looks like, but it's just standard JavaScript where I'm creating test accounts and I'm just passing them in through the function and making function calls. So it's saying, I started this job and now I'm going to check each of your functions. So this is the user, the admin launching the contract. Remember, it's Buffy that wants to party. So Buffy launches our contract. And then we run a few of our functions. We make a reservation. We make our reservations, right? And now we wait until our deadline. And then we allow our users to actually check in. We say we check in this user. They did show, they didn't show. And now here we're catching an error from the back end. Remember, host check-in had an assertion that you must register to call this function. Right here, host check-in. If you try to check in and you're not in my list, return that you have no reservation, continue to operate your application. So it'll say, Jonathan tried to show up and assertion failed. He had no reservation. And we'll come down here and see, I expected this. This is a test case that we wrote on purpose. It'll say expected true, no reservation, and then the name of the user. We'll look at a few of them that did check in, they did show up, and then look at our transfer pattern. Does the transfer occur the way that we expected it to occur? And the answer is yes, right? We see that we've gotten the transfer that we look for based on whether or not the user has actually checked in to our application. So that is our full-scale production level implementation of our RSVP application. I've said a lot today about building Web3 apps. I've said a lot about how Reach makes it more simple in the way that you think about building these decentralized applications. And why? Because we are that blockchain development platform that's designed with all of these special considerations in mind. We knew what you needed to build blockchain applications, and we knew what it was going to take to get to the next level of real world-changing blockchain applications. And we want to give you those tools, give you the power. We want to lower the barrier to become a Web3 programmer, because we feel like doing so will take blockchain mainstream. It will take it to a place where we can actually build the real applications that will make the world-changing events that we know are possible with blockchain. We just need to help it get there. So thank you, everyone who has been here for the duration. I really appreciate your time. I hope you can tell how passionate I am about what I do and about building and innovating in this space. It's exactly what I love to do, and I love to help you get there. So please, if you like what you hear today, install Reach. Start working through the documentation. Work through some of the tutorials. Join our Discord channel. I'm in our Discord channel and answering questions, troubleshooting issues, helping you launch applications. Reach out to me directly. I use my real name and everything because I love what I do and I stand behind my work 100%. Please reach out to me. I want to help you get there. Okay. So thank you everyone for your time. That is Reach and why we would use Reach to build decentralized applications. I'm going to stop talking there now and check through our chat, see if we have any questions. Otherwise, I really appreciate everyone's time, and I look forward to seeing you again in future workshops. Thank you, Bronson. I see you. I see you. Thank you. Thank you so much. Yep. Thank you. A lot more material around this RSVP coming, level 2 stuff like advanced, get you really ready for that like employment level. All right. We're ready for you. So thanks again.